Hello grade 11s and welcome to question number 6, which is a question on acids and bases. As normal, I do encourage you to first try these questions before working along with me to see if you're on the right track. This question says, grade 11 learners want to prepare a standard solution of oxalic acid, that is H2C2O4. They use 15,75 grams of hydrated oxalic acid crystals in order to make a solution of concentration 0,5 mole per decimeter cubed. They prepare the solution in a volumetric flask. They have different volumetric flasks, 250 centimeters cubed, 500 centimeters cubed, and 1 decimeter cubed volumetric flask available. Question 6.1.1 says define concentration. So for 2 marks we say concentration. In answer to question 6.1.2, define concentration. For 2 marks we say concentration is the amount of solute per liter of solution, or you can say it's the amount of solute per cubic decimeter of solution, because a liter is a cubic decimeter. Question 6.1.2 says, which volumetric flask should they use? Show by calculation how you arrive at your answer. So in this case, we know the concentration and we know the mass of the hydrated oxalic acid crystals. So what we can do is we can say concentration is equal to mass divided by molar mass multiplied by volume. Now, in order to calculate the molar mass, we're going to be calculating the molar mass of the hydrated oxalic acid. So that is this formula over here. It's going to equal to 2, because there are 2 hydrogens, that's 1 plus 1, plus 2 times 12, because there are 2 carbons, plus 4 times 16, plus 2 times the molar mass of water, which is 18. And that gives us a final answer, 126 grams per mole. So the mass of the oxalic acid crystals is going to equal to 15,75 grams. The molar mass is 126. We do not know the volume, but the concentration is 0,5. So we can multiply up by 126 times V. We divide by 0,5 times 126, and we find that the volume is equal to 0,25 decimeters cubed. Now 0,25 decimeters cubed means exactly the same thing as 25 centimeters cubed. And therefore, in answering the question, we can say they should use the 250 centimeters cubed volumetric flask. Over here, marks are going to be awarded as follows. You're going to get 1 mark for your formula, 1 mark for the substitution on the left, 1 mark for that on the right, and 1 mark for your final statement that they should use the 250 centimeter cubed volumetric flask. We now go on to question 6.1.3, which says, the learners wish to change the concentration of a small amount of this acid to 0,2 mole per decimeter cubed. To do this, they place 25 centimeters cubed of the acid in a beaker and they add water to it. So what are we doing? We are diluting the solution. How much water must be added to give the required concentration of 0,2 mole per decimeter cubed? So what is happening is we have this concentration of solution in a 250 centimeter cubed volumetric flask. What is going to happen is they're going to transfer this to a beaker. So over here is my beaker. They're only going to transfer 25 centimeters cubed from here to there. So here is the 25 centimeters cubed. The first question we're going to ask ourselves is, when we transfer of the solution to the beaker, what is the same between these 2 solutions? The correct answer is that the concentration here is equal to the concentration in the beaker. Think of it like a glass or big jug of Oros. If you take Oros and pour it into a glass, you're going to find that the taste of the Oros in the jug tastes the same as the Oros in your little glass. And that is not because the number of mole is the same or because the volume is the same, but because the concentration is the same. Now they say, after this, what is going to happen is we're going to add more water to this beaker. So the beaker originally had this amount of water or this amount of solution, but now we're going to add more water to the beaker. We're interested in finding out how much volume is added. But we know that we're going from a volume, number 1, of 25 centimeters cubed to a new volume. Sorry, I see in the previous question I made a mistake. This should be 250 centimeters cubed. That was a mistake. I do apologize. 0.25 decimeters cubed is the same as 250 centimeters cubed. So concentration in 1, we know in the first case the concentration is the same as here. It is 0.5 mole per decimeters cubed. In the case where we've diluted it, we've changed the concentration from 0.5 to a new concentration of 0.2 mole per decimeters cubed. We don't know the new volume, but we know that as we go from case number 1 to where we add water, the number of moles is the same. The number of particles of, in this case, we're dealing with the oxalic acid, that is going to be exactly the same. All that we're changing is the volume. And as a result of us changing the volume, the concentration changes. So we know in case number 1 and case number 2, the number of moles is equal. So we write down number of moles on the left is equal to the number of moles on the right. Since number of moles is concentration multiplied by volume, we can say that the product of the concentrations and the volumes are the same. On the left-hand side, we have a concentration of 0.5. The volume is 25 times 10 to the negative 3 decimeters cubed. The concentration on the right-hand side is 0.2, and we would like to find the new volume of the entire new solution, the diluted solution. Plugging all of this into our calculators, we find out that the volume is 0.0625 decimeters cubed. If we multiply this by 1000 or multiply by 10 to the power of 3, we know, and this is unnecessary, but we know that this is 62.5 centimeters cubed. So the question asks specifically, how much water must be added? To find out the amount that is added, we're going to take the volume of the diluted solution and we're going to subtract the volume of the initial solution. So we're going to say V added is equal to V2 minus V1. That is going to be 62.5 minus 25 centimeters cubed, or if you'd like to work in decimeters cubed, that is also okay. And in the end, 62.5 minus 25 gives us a final answer of 37.5 centimeters cubed of water being added to the beaker in order to dilute the solution to a solution of 0.2 mole per decimeters cubed. This question is out of 4 marks, so marks are going to be awarded as follows. You're going to get 1 mark for your formula. This formula is not on your formula sheet, but please make sure that you first state that the number of moles is equal. This is a manipulated form of the formula C is equal to N divided by V. Then you're going to get 1 mark for your substitution, 1 mark for subtracting your initial and final volume, or your initial volume from your final volume, to find the amount that is added, and that is your last mark. So this is out of 4 marks. Now we can move on to question 6.1.4, which says the standard solution is used to titrate a solution of sodium hydroxide. Write the balanced equation for the reaction taking place here. So what is going to happen is we're going to take sodium hydroxide, NaOH, and we're going to titrate it with this oxalic acid, which has the formula H2C2O4. Oxalic acid is diprotic, which means it has the ability to donate 2 protons. Remember that when an acid reacts with a metal hydroxide, it forms a salt and water. So firstly, we're going to write out the water. The question becomes then, what is the salt? Well, the water formed from the hydroxide of the base and the hydrogen from the acid. We're left with C2O4, which has a charge of 2 minus. If the two hydrogens provided a charge of 2 plus, then this part has a charge of 2 minus. The sodium, being in group 1, has a charge of positive 1. So that means we're going to need 2 sodiums to bond to the C2O4. And the salt is therefore Na2C2O4. Okay, and now we just check to see if it is balanced. I'm going to get rid of these charges because you're actually not allowed to write down the charges. And we see on the left hand side we have 1 sodium. That's a problem. So let's go and put a 2 in front of the sodiums. Now we have on the left hand side 4 hydrogens. So let's go put a 2 in front of the water in order to balance the hydrogens. And if you now go ahead and you add the oxygens, the hydrogens, the carbons, the sodiums, you're going to find that the equation is balanced. So you can get 1 mark for your reactants, 1 mark for the correct products, and lastly a mark for balancing the equation correctly. So this brings us to the end of this video, but not the end of question number 6. So please be sure to join me in the next video where we're going to continue with question number 6 on acids and bases.